Welcome back to the Explainer. Today, we are jumping right into the absolute bedrock of data science. We're going to strip away all the noise and synthesize the essential mathematical building blocks of machine learning, summary statistics. It's time to upgrade our foundational toolkit.
Think about this for a second. How do you actually summarize an infinite number of possibilities using, just a couple of numbers? In data science, this is known as the problem of density estimation. We're faced with this chaotic, infinite universe of possible data, and we somehow need a way to condense all of that down into digestible, manageable summary statistics. Here is our game plan for today as we systematically scale up. 1. Summarizing the unknown. 2. Expectation. 3. Variance. 4. Covariance. 5. The covariance matrix. And finally 6. The machine learning connection. Let's kick things off with part 1. Summarizing the unknown.
It's kind of like being a detective, right? We're using statistics as clues to uncover the true hidden shape of a dataset. But here's the catch. When we try to model a probability distribution from just a finite set of observations, the problem is fundamentally ill-posed. What that actually means is there are literally infinitely many candidate distributions that could have produced the data points we're seeing. Because we can never, ever see every single possible data point in existence, we have to rely on summary statistics. These descriptive properties are our main tools to map out and model the unknown. Moving right along to part 2, expectation, finding the center. Let's meet the first major heavy hitter in our toolkit, expectation. This is what helps us anchor our understanding of a single variable right in the center of a one-dimensional space. Mathematically, expectation is the average value of a function under a probability distribution, but honestly, it's way easier to just picture it physically as a center of mass. It's essentially a weighted average. The relative probabilities act almost like gravity, pulling that center of mass directly toward the values that are most likely to occur. Now, depending on the type of data we're looking at, the mathematical notation shifts slightly, though the underlying concept is exactly the same. Whether you're dealing with the rigid, distinct steps of a discrete summation, like rolling a pair of dice, or the smooth, flowing curve of a continuous integral, like mapping temperature changes over time, the mission is totally identical. Find that mathematical center of gravity. But here's where it gets super interesting. Expectation, or the mean, is really just one version of the center. Imagine a horizontal bimodal distribution, basically a curve that has two distinct peaks. In a setup like that, the mean, which is our expectation, the median, the literal middle value, and the mode, the most frequent value, can all end up in completely different places. The expected value is a linear operator, sure, but it might actually fall right into a totally empty valley between those two peaks. Okay, part 3, variance, measuring the spread. Once we've nailed down our center, we need to understand the spread. That's where variance steps in. It measures how tightly packed or how loosely scattered our data is around that center point. Technically, it captures the expected squared error if you were to use just a single observation to estimate the mean. Oh, and a quick crucial side note here. If you take the square root of the variance, you get the standard deviation, which is another incredibly vital metric we use all the time to describe that exact same spread. Let's break down the physical intuition of how we actually calculate this. Step 1, you find your mean. Step 2, you measure the distance of your data points from that mean. And step 3, this is key, you square that distance. Why square it? Well, by squaring the distance, we are aggressively penalizing large outliers. A single extreme data point sitting way out far from the mean will totally blow up your variance, making this statistic highly sensitive and honestly sometimes a bit fragile to the extremes in our dataset. Which brings us to part 4, covariance, variables moving together. Now we're leveling up to 2 dimensions. We aren't just looking at variables sitting in isolation anymore. We want to see how they dance together. Covariance expresses the extent to which 2 random variables vary with each other. We calculate it by looking at the expected product of their deviations from their respective means. If 2 variables are completely independent, their covariance completely vanishes to 0. But if they are linked in some way, the covariance captures the direction of that relationship. The thing is, raw covariance can be a bit of a headache to interpret, because its scale depends entirely on the variance of the variables themselves. To fix that, we use correlation. Correlation is simply the normalized, standardized version of covariance. It is strictly bound between -1 and +1. A positive correlation means as one variable grows, the other is expected to grow. A negative correlation means as one increases, the other decreases. It's just a beautifully clean way to measure that relationship. All right, part 5, the covariance matrix. So we've mastered one dimension and we've got pairs down. Now we are stepping into vast, high-dimensional vector spaces. You can think of the covariance matrix as your ultimate cheat sheet for multidimensional data. When you have a random vector with a bunch of coordinates, this matrix is an n by n grid. Right down the diagonal of this grid, you're going to find the marginal variances of each individual variable. Everywhere else, all those off-diagonal entries contain the covariances between every single pair of those variables. It maps out the entire web of relationships for us. And this matrix has some seriously elegant mathematical properties. It is symmetric and it is positive semi-definite. But here is where the math turns into an absolute superpower for data scientists. If you analyze the eigenvectors of this matrix, the top eigenvector, the one with the largest eigenvalue, literally points in the exact direction where the data spreads out the most. This right here is the mathematical foundation for principal component analysis, revealing the primary directions of variance in really complex data. Finally, part 6, the machine learning connection. Let's tie all these theoretical building blocks back to reality. Why does this actually matter for machine learning? Well, enter the magic of the central limit theorem. It tells us that as our sample size grows, let's say we're observing random variables to find an error rate, the distribution governing the sample mean actually approaches a normal, bell-shaped distribution. And the crazy part? This happens even when we have absolutely no idea what the shape of the underlying distribution is. Because of this, we can use our sample expectation and sample variance to confidently estimate true population parameters. On top of that, these exact same summary statistics are the core of how we measure error in our models. The expected squared difference between our model's prediction and the true function can be broken down into two main pieces, bias squared and variance. Bias is the extent to which our average prediction misses the true function. Variance measures how wildly our model's predictions jump around depending on the specific training data we feed it. So at the end of the day, optimizing a machine learning model is quite literally just an exercise in balancing expectation and variance. So let's do a quick recap of this toolkit. We have expectation to find the center, variance to measure the spread, and covariance to map the relationships. These summary statistics, these descriptive properties of distributions, are the absolute bedrock of probabilistic modeling. But before we wrap up, I want to leave you with something to really chew on. Remember earlier how we saw that the mean could fall entirely inside an empty valley of a bimodal distribution? Well, if these summary statistics are aggressively compressing infinite realities down to just a couple of numbers, what vital hidden patterns in your data are you erasing without even knowing it? It's a question that definitely demands some more advanced modeling down the road. Thanks so much for joining me for this explainer, and I'll catch you next time.